chapter 9 is about center of gravity and centroid, and in this chapter we will study what is center of gravity, what is center of mass, how we calculate the centroid of a volume, area or line. And these are one of the most important concepts, if not the most concepts, in engineering mechanics statics. And the last section would be on composite body. So if you have a body which is composed of different type of shapes, then how to calculate the centroid of a volume we will investigate in section 9.4. So what is a gravity? Now, the center of gravity by definition is an imaginary point where the whole weight of the body is concentrated. So imagine if you have a rigid body and there is an imaginary point where the whole weight of that rigid body is concentrated, then that center point, imaginary point, would be called as center of gravity. For example, we have a rigid body and that body is composed of many particles, and each particle has some mass, and that mass is, if that mass would be in a gravitational field, then there would be a weight acting on that mass of a particle. So you have different particles and all the particles have this weight, and if you want to calculate the overall weight of the rigid body, so it would be simple, right? You have different weights of all these particles, and if you integrate all those weights, then you will get the total weight. So summing all the weights of those individual particles, you will get the total weight. Now, what we are interested in is to calculate the center of gravity, which is a center point, imaginary point, where the whole weight of the body is concentrated. So let's just say it would be somewhere here. So this is that imaginary point where this total weight of the body is acting. Now, why this center of gravity point is important is because it is used to locate the center of weight of that object. For example, this is that imaginary point, and in that imaginary point this rigid body is balancing out itself. So all the moment on the right side is equal to all the moment on the left side. So this point is called the center of gravity. So if I will try to balance this in some other point, it will not balance. It will only be balanced at its center of gravity. Now, this center of gravity is important for many applications, but what we are interested in is to calculate or to quantify this center of gravity distance. So what we are interested in is that we need to know that where that center of gravity point lies. So we are interested in this distance, because if we know this distance, then we can calculate the imaginary point, which is the center of gravity. So let's just go through and try to quantify how we can calculate this center of gravity. So we have to go through the mathematical definition of center of gravity. Now, the mathematical definition is that the location of center of gravity can be measured along any axis. So let's just say we want to calculate this along y-axis. So this would be the y-axis. So if maybe this is the y-axis, so that distance we are interested in, and if we know this distance, then we can get an idea that where that center of gravity of this rigid body lies. Now, how we can calculate? We can calculate by equating the moment of W. So we studied moment in the previous lecture. So if we calculate the moment, like for example, I was discussing a while ago that the moment is where it balances out. So basically the moment, if we can equate the moment, then we can calculate this center of gravity point. So that's the equation for equating moment. So this mr is the resultant total moment at along y-axis, and that moment would be equal to summation of moments of all the individual particles. So let's just say you have different particles, and if you want to equate the moment, then by equating the moment you can calculate this imaginary center of gravity point. Now, how to equate? Let's just say this is the same two-dimensional rigid body, and this rigid body is composed of many particles or points. So all these particles will have a weight dw. So how to calculate the total weight is that if we have these individual weights, and we know the distance of these individual weights to some reference point. So if we integrate all these reference points with the weights, then what we will get is total weight and the distance, and this distance is the center of gravity distance. So if I put it in a denominator, so that's the equation. This is the equation to calculate this center of gravity. Now we know this weight is composed of smaller weights. So all these smaller weights integrated becomes the total weight. So we have to sum up all the individual weights which are acting on all these particles, and if you sum them up or integrate them, then you can calculate the total weight. So this is the final equation which we can use to calculate the center of gravity. Now, if we have a volume, because previously we were studying calculating the center of gravity for two-dimensional rigid body. Now if we have 3 dimensions, then similarly we can calculate the center of gravity for point for all these 3 dimensions. So this would be equation for x, y and z dimension. So all we have done is that replace this x, y and z, and we can calculate this center of gravity from any reference point. So if we have a 3-dimensional space and we know the rigid body, so we can calculate the center of gravity by using these 3 equations. Now this center of gravity can be calculated when this rigid body is in a gravitational field. For example, this center of gravity would be different in Earth, different in Moon, and if someone is in space or some object is in space where there is no gravitational field, then this gravitational center of gravity would no longer exist because there would be no weight. But this object has mass. So sometimes if we want to calculate the center point without influencing the center of gravity, then we can use this center of mass. So what is center of mass? Center of mass is again an imaginary point where the distribution of mass is equal in all directions. Now if we want to calculate the center of mass, because center of mass would be constant on Moon or Earth or anywhere in the universe, so sometimes we are also interested in calculating what would be the center of mass, because that would be constant and that will not have an influence of gravity. So let's just say again we have a rigid body with so many points. Now this center of mass would be such a point where the distribution of mass is equal in all directions. So what we are trying to explain here is that it is a center of a mass. So all the distribution on all the sides of this rigid body would be equal. So that's the center of mass. Now we know that weight is equal to mass into g. So if we assume that the gravitational field is constant, so value of g is constant, then we can simply just, instead of dw, we can put g dm. So we know that the center of gravity formula was x dw over summation of dw. So we know dw is gm and g is a constant factor, so we can constants can go out of the integral, and once this w would be equal to mg, and g can come out and it will cancel out. So you can get the equations for center of mass by just equating this g and cancelling out. So this would be the equations for calculating the center of mass. Now what is a centroid? Centroid is again an imaginary point, but this is an imaginary point where the geometric center of the body lies. Now this is about geometry. Now center of weight was a property of a rigid body where it was also under the influence of gravitational field. If we take out the influence of the gravitational field, then we can calculate the center of mass. Now, what is center of mass relationship with the volume? Now we know that density is equal to mass over volume. Now if we assume that the mass is also constant, it means that it is the same material, then we can also equate the mass out and we can cancel the mass out, and then the only thing will be remaining would be volume. Now this is very important property in engineering mechanics, and it's used widely in so many applications, because now we don't need to know what is the gravitational field, we don't need to know what is the material composed of, unless and until it's the same material and the gravitational field is constant. We can make use of this centroid of a volume, which is also much easier to calculate as compared to other two properties, and we can use it in our engineering mechanics applications. Okay, so similarly, we know if we assume that this mass is constant, so we can take the mass out and cancel out, and then we can calculate this centroid of a volume equation. Now later we're gonna just simplify this and put one equation to calculate the centroid of an volume or area, but for now you need to understand, like, that's how roughly we can get the equations to calculate center of gravity, center of mass, or even centroid of a volume. Similarly, if we want to calculate the centroid of an area or centroid of a line, we can just replace this volume with area or with line, then we can calculate the centroid of even an area of a line. Now, important thing to note here is that the centroid coincides with the center of mass and center of gravity if the material composing of the body is uniform or homogeneous. Now, all they're trying to say is that if you have a constant gravitational field, then obviously the center of weight and the center of mass would coincide. So basically they are the same point. Now, if the mass is also constant, by constant I mean it's homogeneous, made up of same material, so whole rigid body is made up of same material, then you don't also not need to worry about the material. Then you can calculate the centroid of volume, and this centroid of volume would be exactly the center of mass and the center of gravity. So if this rigid body is following this assumption, which is uniform and homogeneous, then all the center of gravity, center of mass, and centroid will be the same point. Okay, so now as we have discussed, we can also calculate the centroid of an area and the centroid of a line by using these equations. Now all these equations which I have mentioned here are actually somewhat the same. That is, they were extracted from equating the moment, which is summation of moment along any axis is the same. So what we did was that if we have to calculate the, for example, centroid of an area, so centroid of an area multiplied by total area is equal to integral of centroid of individual area. So that's how you calculate the centroid of an area. So you have all these small areas, and you have the centroid of all these small areas from a reference point. So if you equate them all, or if you take an integral, then you will have a total area, because if you take an integral of all the small areas, you will get total area. If you take a moment that is multiplying that small areas with the small centroid, then you will get an overall area and an overall centroid. So all you have to remember here is this equation to calculate the centroid of an area. Similarly, if you want to calculate the centroid of a line, it would be pretty straightforward, and you can calculate by using this. So this area is basically an integral of all these small areas. So once we will do the example, then it will become much clearer that how we can calculate this centroid of an area or other properties. So before going and calculating the centroid of a composite body, let's just try to understand how we can calculate centroid of a simple shape. Now, for example, if there is some triangle, we can imagine that the centroid would be somewhat a center of this square of a rectangle. So for example, the height of a rectangle is h, then we know that the centroid is located at half the distance of h. Similarly, if we have a circle, we know that the centroid would be at the center of a circle. But what about triangle? How we can calculate the centroid of a triangle? Now, how you know where is centroid intuitively is that we know that centroid should be somewhat at equal shapes from each other. For example, the area above the point and below the point should be equal, or the area to the left of the point to the right of the point should be also equal. So that's how you know that it's somewhat at the center. So this is a centroid. Now for triangle, we know if we try to divide the area below or top, so we know that it's not at the h, but if this is h, we know that this is not by h by 2 because it would be somewhere below, because the area at the lower side is more. So how to calculate this? Now we don't need to remember all the mathematical formulations to calculate this, but all we need to know is the final result. And once we know the formula to calculate the centroid, then we can calculate the centroid of any other shapes as well. So usually people already know, we already know for rectangle what is the centroid, for circle what is centroid, and we also know for a triangle what is a centroid, but we will calculate this here just for the sake of understanding that how we can calculate usually centroid of simple shapes. So we know the formula. If we want to calculate from x-axis that what is the centroid, let's just say this is the centroid. So all we need to know is this distance, and I call this distance y, which is written here. So we know what the formula. The formula is we have to integrate all the small areas and the distance of these areas to that reference point and divided by all the area. And this area is basically we have to integrate from 0 to h. 0 to h we have to integrate. Now what we need to know is this dA. So area is, this is the dA part. Now area is length, which is x, into height, which is dy. So if we can know x, then we can put it here, and then we can calculate the centroid distance of this triangle. Now x can be calculated by using slope. So if we say this b divided by h, so b divided by h is a slope, so we also can equate this with this divided by this. So x is, this is x, so height would be h minus y, this distance, because this total is h, and h minus y, you will get this. So from here you can calculate x, which would be equal to b by h into, this will go there, h minus y. So you put this here and you can calculate dA, and dA would then be equal to b by h, h minus y, and dy. Now we have calculated this dy, we can put it in the equation and we can calculate this y. So y would be equal to integral of y, and this dy is equal to b by h, h minus y into dy. Now you don't have to remember these mathematical formulation. I am just interested in calculating what is the final centroid distance formula, and once we know the formula, then we can use the formula directly. So this would be equal to h minus y dy, and if you integrate this from 0 to h, and this is also 0 to h, then you will get 1 by 6 bh square over 1 by 2 bh, and this is equal to h3. So what I am trying to say here is that the distance of centroid for a triangle is h by 3. So this is what you all have to remember. So if you know the height of a triangle, you just multiply, divide by 3, and then you can calculate the centroid of that triangle. So centroid of a triangle is always h by 3 from here and b by 3 from here, so somewhat somewhere here you can calculate the centroid of a triangle. Now, usually we already know the centroid of simple shapes, but what we are interested in is to calculate the centroid of a composite body. So how we can calculate the centroid of a composite body in case we have this shape, let's just say, and we are interested to calculate the centroid of this composite body. Now, one way to calculate the centroid of this composite body is to divide this composite body into simpler shapes. For example, let's just say this body is 1. This is also a square, and this square would be a segment 2, and this square is segment 3. So if we know the centroid of segment 1, and we know the centroid of segment 2, and we know the centroid of segment 3, so we can calculate the centroid by adding 1 plus 2, because these are two, this is 2 and this is 1, by adding and subtracting 3. So if you subtract 3 from 1 to 3, you can calculate the centroid of this composite body. Okay, so how to calculate the centroid? Let's just see what was the formula. So if we want to calculate the centroid, we need these two formulas, which is over summation of A, and y bar is equal to this summation of A. So previously we know that in order to calculate the centroid, we used to integrate the areas. So since this is a discrete shape, so instead of integrating, I have replaced it with summation sign, but it means the same thing. So if we know these two values, if we know summation of area, if we know summation of in this moment of area, then we can calculate the centroid. So first thing to know is the segments. Now what are the segments? We have segment 1, 2, 3. And what are the area of these segments? Now what is the area of segment 1? Segment 1 is 3 meter, and this is also 3 meter. So the area of triangle is 1 by 2 into 3 into 3, which would be equal to 4.5. And the area of segment 2 is length into width. So length is 1.5, 1.5, 3 and 3. So you have length 3, you have width 3, so you will get 9. And this is the segment 3, and the area of segment 3 is also, this is 2 feet into 1 feet. So 2 into 1, the area is 2. But since we need to subtract the segment 3 from 1 to 3, so we will put a negative sign. So now we have areas of all these, and what we were interested in was summation of area. So what is summation of area? So you have to add all these, and if you add all these, you will get 11.5. So this is the area. Now the second thing was to calculate the x and y distances. So this is our reference point x, this is our reference point y, and we have to calculate the centroids of individual shapes from these reference x's. So if this is the shape 1, and what would be the distance from y-axis to this centroid? We know the centroid of a triangle is h by 3. So what is h? It is 3. So 3 by 3 is equal to 1. So 1 is the distance from y-axis also, and 1 is the distance from x-axis also. So our centroid for triangle is 1. What is the centroid for this shape segment 2? So from y-axis, the distance is 1.5, but it is negative 1.5 because the x-axis is negative from here to here. And the pause from x-axis, you have a distance 1.5 positive. So from x-axis you have negative 1.5, and from y you have positive. So from y you have positive. And similarly for shape 3, from y what is the distance of centroid? The distance is 2.5, and from x the distance is 2. So we will put minus 2.5 because it's negative from x, and 2 which is positive. Now what we need to calculate is summation of xa. So summation of not xa, and then we'll calculate ya. So we will multiply x with a and multiply y with a. So if we do that, we will get 4.5, 13.5, which is negative because, and then you have 5, and for y also 4.5, 13.5, and minus 4. Now it will become clear now why I am multiplying these things, because I am interested in calculating summation of a, which I have already calculated, and I am interested in calculating summation of xa. So first we'll calculate xa and then we'll do the summation. Now let's just do the summation. So if you add all these three quantities, you will get minus 4, and if you add all these three quantities, you will get 14. Now what was the formula for xi? It was summation of xa over summation of a. So what is summation of xa? This is the summation of xa, minus 4. And what is the summation of a? This is summation of a, which is 11.5. So if you do the maths, you will get minus 0.348 feet. And similarly for y also, if you do, you will get 1.22 feet for y. And for x, we got minus 0.348. Now, this was, I'm just gonna draw the shape of composite body. So this is the composite body, and this was the y-axis, and this was the x-axis. Now where is the centroid of this composite body? First we have to go negative 0.348 from x-axis, so from y-axis, because this is distance x. So this is minus 0.348, and from y we have to go positive, so we have to go upward, and the distance should be 1.22. So if we calculate, so this is the centroid of the composite body. So that's how you can calculate the centroid of composite bodies, and this is one of the most important property in engineering mechanics, which we will use in coming lectures. So this was lecture 9, and see you in the next lecture.